Welcome, everybody. So sometimes people still file in, but I think we should start promptly. So I wanted to say a few words by Cal Kieval, who was a professor of mathematics here at HSU. And he retired long before I came, so I never got to meet him. But he was quite passionate about undergraduate education, and he donated quite a bit of money to HSU and to a couple of other institutions, too. So he established a scholarship program after his retirement in 1979, and then after his death, they actually established an endowment that's paying for the lecture series and that's continuing to pay for the scholarship. Renovating a classroom on campus is 2 months tall, and he funded a sundial, so he really gave a lot of money to HSU. He also established a lecture series at Cornell University, where he got his undergraduate degree, and also at Southern Oregon University. That was in his hometown after he retired. And our speaker actually has been the Kieval lecturer both here now and at Cornell, which I didn't know until today. So I'm going to turn it over to our provost to introduce our speaker, but I'm going to say a few words about Alon. So Provost Amit came to HSU in 2016, and the first thing that I realized when I heard his name is that he's obviously chair of cultural heritage, and turns out to be true, so he's of Hungarian descent, as I am, and I think you're second generation, third? So Provost Amit came to HSU from 2016, like I said. He was before the Dean of College of Arts and Sciences at Western Michigan University, where he had been since 1993. He holds a PhD from the Pennsylvania State University in plant biology, and he's found various institutions. So Alex, would you please start by giving us a
Great. It's my distinct pleasure to introduce the speaker here, Dr. Chris Ferris, who's joining us this evening all the way from Santa Clara University, and he serves as professor of mathematics and computer science at Cal. Dr. Ferris holds an undergraduate degree from Pomona College, and he also holds a PhD from MIT, which was awarded in 1981. And he has numerous awards and recognitions, sort of, I'm taking all full scale charts now, that include the Distinguished Teaching Award from the Goldman section of the SAA, and the Best Photograph, Painting, or Print at the 2018 Mathematical Art Exhibition at the Joint Mathematics Exhibition. And that part got me a little bit curious. So I began to look, as I prepared for this evening, at this book called Creating Symmetry, the Artful Mathematics of Wallpaper Patterns, published by Princeton University back in 2015 by Dr. Ferris. And as I dug into a little bit of information about this, I discovered a couple of book reviews. So I'm going to read 2 book reviews. The first one, I'll just talk about it. What does it say about the book? Creating Symmetry begins by addressing the enigma of a simple curve, whose curious symmetry seems unexplained by formula. Dr. Ferris describes how complex numbers unlock the mystery, and how they lead to the next steps on an engaging path constructing waveforms. As a plant biologist, I wasn't quite sure how to decode that. So I began to read the reviews. The first one is by Paul Zorn. He's the author of Understanding Real Analysis. I suspect this person will know what we're talking about. This book introduces readers to the fascinating interplay of geometry, complex function theory, abstract algebra, complex domain coloring, Fourier series, and aesthetics, for producing really beautiful images. That part I caught. Professor Ferris shows how structured forms of symmetry can be constructed in a disciplined way from the first mathematical principles, and how artistically pleasing images can communicate result is a set of algorithmic tools for transforming ordinary photographs into rosettes and wave-like murals decorated with colorful swirls and gradients. It is difficult to imagine a more engaging focus for teaching the mathematics of symmetry. So the word I wrote down was, wow. So what an incredible review, praise, and appreciation for this wonderful book. So please join me in welcoming Dr. Ferris to Humboldt State this afternoon, gosh, time shifted here, to deliver the 2019 Spring Kieval Lecture. So, welcome.
Thank you. Thank you. I'm delighted to be here. Yes, I asked for the lights to be turned down. Better that you should look at the screen than look at me, because what I really have to show you is up there. I've been very gratified by the good reviews of my book and really by the overall reception of my work, which has surprised me. Symmetry is a very old topic, and I found it hard to imagine that I would find something new to say about it. Well, I'll tell you how I found that. I even have like any good superhero, I have my origin story to share with you. So, it looks visually to me as if I'm addressing mostly mathematicians here, but my remarks are very much planned for the non-mathematician. So I'm going to begin by asking what the word symmetry means. So we can all, go back with beginner's mind and think about what it might mean to have something be symmetric. Well, I asked our art historian at Santa Clara way back in the 90s, I said, what does symmetry mean to you art historians? And she said, oh, it's like two sides of your face being the same, or two sides of a butterfly wing. And I thought, oh, is that what they think? And yeah, this is the front of our mission church. And if you've never visited Santa Clara University, Jesuit university built on the site of one of the Santa Clara missions, I highly recommend it. But you'll see that this building enjoys that feature of symmetry. Like, ignore the tower and the little side building there, and the two sides really are the same. That has reflective symmetry, I would say. And why did artists maybe get into using this as a pleasing device? I believe that it's because we saw this in nature quite a lot. So here's a beautiful flower. You all know the Mariposa lily. They probably grow around here. You can see that has two halves the same. Well, that actually has another kind of symmetry too. That comes in three parts the same. And if you go inside the mission church, you can see that some decorative artist has had that idea and implemented it as a decorative pattern. So here's a thing with four parts the same. And I'm going to call that a rosette. Also in the mission church, it's got this beautiful historic painting. The church is actually a restoration from the 30s, but still it's painted in the old mission style from the mission days. And here is a thing where you see some sort of florets there with four parts the same, but then those themselves are repeated side to side. And this really does continue for quite a long band, and you could theoretically continue that pattern forever. And I'm going to call that kind of pattern a frieze. Also inside the mission church, is a pattern like this. That's not very much of the pattern, but you can imagine that it repeats forever to the left and right, and you could even repeat it up and down as well to get a sort of checkerboard-like pattern with the potential to fill the entire plane. So my message for you tonight is that mathematics gives us great tools to create symmetry, and there are many things that other people have done before me, but I have a distinctive toolkit to share with you. And it's going to create things like this, a rosette. This one has 5 parts the same. It allows us to create things that repeat infinitely side to side, frieze patterns like this, and the potential to create wallpaper patterns. This actually is made from the wisteria at Santa Clara University. I'll be telling you more about this, but I've been bragging as I see your little wisteria vines out here that we have one that's 150 years old. You can't put your arms around it. It's extraordinary. So this is what I'm going to tell you about this evening, is how mathematicians have tools to create symmetry. The concept of symmetry involves sameness. Is it the same side to side? Is it the same repeating left to right? Is it the same repeating in many directions? But it's all involved with the concept of sameness, and the mathematical term for this is invariance. So I'm going to speak of patterns that are invariant under certain transformations. So here's my origin story, is that in the 90s I was teaching survey of geometry out of a book, and I was just appalled by the definition of what a pattern was. In a survey of geometry we teach theory of patterns, and it said a frieze pattern is a set of points that is invariant under, and then described the transformations that it's invariant under. And I thought, set of points? Set of points? How, what? And the diagrams all looked like that. So yeah, this is an example of a certain frieze. Like I want you to imagine repeating, that is one full cycle from one right side up F to another right side F, and repeat again and repeat again. It's got this other interesting symmetry that you can flip and slide. Flip and slide, and the pattern falls into coincidence with itself. But, you know, so the set of points are the points that are black there. And so I thought, set of points, no, that's not what a beautiful pattern is. I wanted to see things that looked like this. This also demonstrates the idea of translation, you know, of continuing, repeating in the same way again and again, side to side. And it's also, if you look, it's got that flip and slide, flip and slide. So I was teaching out of this book. I never thought that that would take over my life for the next 25, 30 years, but yeah, it did. So here's another thing about pattern, is that when I decided I was really interested in patterns and wanted to study them more, I read in the big Bible of patterns that a pattern is obtained by repeating a motif. So a motif is a piece, then you repeat, 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 repeat. And so I thought, yeah, great, if that's your definition, you just do that. Carve it in a potato and go stamp, 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 stamp. You got a pattern. 5 copies of a motif. No, I want my rosette to look like that. Yeah, it's true that you could take a pie slicer and cut out 72 degrees of that and repeat the pattern from that. It's not that there is no motif, but it's that the motif isn't the thing you notice. That's not what you notice. The thing you do notice is the invariance. When you turn this thing by 72 degrees, the pattern falls into coincidence with itself. So I, over the years developed this response that no, patterns aren't that. They're not made by stamping out copies of a motif. They're made from waves. So I come from the land of smooth mathematics where we study waves, waves. You can imagine waves on the ocean. And I decided that's how wallpaper should be made. So I've developed this technique where you can take a photograph like this and use a process of complex valued wave functions and turn that into a pattern that looks like this. You might think that there are parts there, you might think that there are pieces to be assembled, but really the whole thing works together as a smooth, wavy, repeating thing. So, and it's really fun to look closely at the detail. So I don't know, I have this personality where I look up there and see the stem of the peach and go, oh, that's so beautiful and dear. And then, my little shoelaces there, becoming a very subtle feature of the pattern here, and the denim of my jeans. So there is this software called SymmetryWorks. It was written by Bowdoin students. It's public domain software. I can give you a little PDF about how to download it, how to play with it, how to learn about it. There's some other commercial thing called SymmetryWorks, but anyway, find me and I can direct you to this. And the whole gestalt here for non-mathematicians is that the reason this is moving for me is that there are, sort of 2 things that I think are beautiful. And one is the astonishing beauty of pure mathematics that sometimes feels sort of cold, and, it's out there, but, it's just amazing. And then the world, I'm very engaged in the world. And so to bring those together in one body of work has been a source of great delight for me these many 25, 30 years. So yeah, please read the details. I'm delighted with this book. Princeton University Press did an astonishing job to make it beautiful and to make it cost $35. It's a coffee table book with color photographs in it. And so yeah, please read the details. Here's what I would like to share with you this evening. So here's a little outline. I want to talk to you about when you look at a pattern, what do you look for in order to analyze it, in order to learn more about it, in order to reveal its symmetry. And then I want to talk about classifying patterns and hope that as you move through your world, you will see patterns and then stop to think, oh, wait, what's going on in that pattern? And I can even tell you there's this goal, a learning goal. If you could learn to classify patterns according to this certain classification, I'd be really happy. And then I'm going to tell you just a little bit about the wave theory. Where, not a math talk, so we're not going to go very deeply into the partial differential equations involved. But I will try and give you a feel for what do I mean by these waves and how do they fit together to make these patterns. And then I have kind of too much to say about symmetry variations and topics that came to me. Some of them are the chapters at the end of the book, and some of them are things since the book was published. I continue to be surprised by how there's always something new. I thought I would say something about this and be done, and then go study something else. And it just keeps opening up with more and more stuff. I'm amazed. So there's a theme that goes throughout this, and it's a theme of freedom and constraint. So that on the one hand, as an artist, yeah, you're free to make all these artistic decisions and choose things to be any way you want. But if you're going to make patterns, then there are constraints. And there are some corners you can get yourself painted into. So that if you're going to have it this way, then you also have to have it this way too. And that's a very interesting tension that I've enjoyed working with in my work. I think every artist understands the idea of balancing freedom of their imagination and constraint of their medium. And that happens here too. So, here's our pattern. What happens when your mind looks at this and says, look, it's a pattern? There's just this concept of repeating and invariance, and somehow this is invariant under doing certain things. And let me highlight for you this concept. I'm having trouble with my clicker, with translational symmetry. I have taken another copy of this and I have moved it, it looks like down and to the right, until the pattern falls into coincidence with itself. Maybe I took that dot and moved it there. But I don't want you just to focus on that one dot. I want you to focus on how all these dots line up with all those dots. And all these little diamonds line up with all those little diamonds. And you might say, oh wait, but the original pattern was a square and this new thing isn't a square. Well, I invite you to engage your imagination and realize that what I showed you at first was a swatch of an infinite pattern. And therefore, as I move this, you can see what's beyond the frame. And I said this in my talk this afternoon. Many of you were there, but it's so important I want to repeat it. There's something about our visual cortex that allows us to pick up a piece of the pattern and move it and see that it is the same in that other place. Why did we evolve to do that? Surely this is the good plant. This is the plant that will nourish me, and I need to carry that memory from one place to another. But it's very deep, and I can't help but say, off script here, that why are we loving patterns maybe more today than 20 years ago? And I feel that it's because the patterns of nature are threatened, and so that we take comfort in something that repeats with sameness. There's a comfort to it. So I call this comfort food for the eyes. Yeah. So I'm going to call this translational symmetry. And that translation that I did when I slide it, that's something I did to the pattern, and the pattern was invariant under that motion. What else have we got? Well, let me draw your attention to this red line. The pattern is the same on both sides of that. And your mind can also pick up the pattern on one side, flip it, and move it to the other side and say, yep, that's a check, that's the same. I'm going to call that mirror symmetry. Performing that flip is called a symmetry of this pattern. And yeah, the mirror reflection is a symmetry of this pattern, and I want to call that a mirror axis. Do you see other mirror axes? We'll be talking about the plethora of them that occur in this pattern. What else have we got? We got rotational symmetry. So let me draw your attention here. And here I've highlighted the rotated piece with a little glow there. It's like I put a pin there and rotated this thing 60 degrees. And again, the pattern falls into coincidence with itself. It matches everywhere perfectly. So here's some vocabulary. I want to call that point a 6 center. Why? Because when you rotate 60 degrees 6 times around it, you've rotated 360 degrees. So you're back where you've started. Did you know that doing nothing to the pattern leaves it alone? Doing nothing is always a symmetry of a pattern. So what other rotational symmetries do you see? Can I get a little audience participation here? What's the next highest order of symmetry here? I'm seeing a 3 center. Yes, if you rotate 120 degrees about there, the pattern falls into coincidence with itself. What else have we got? Twofold rotational symmetry, and there is a 2 center. So here, I think, is an interesting question for you. What if I wanted to be the most creative person in the world, and I wanted to create wallpaper with 6-fold rotational symmetry, but I didn't want to have any of that 3-fold symmetry, none of that 2-fold symmetry. I don't like that. I want to have it just my way. We're going to find out. But that's an interesting question. And then I have to tell you, this is made of stained glass, and it looks like stained glass. But I think I have a little more of it to show you here. Sometimes people say, oh, that looks like a kaleidoscope. And you can't get a kaleidoscope to do a curve like that. And see this texture of that yellow glass in there? It's just, there's something really visually different about the method of producing these patterns. So, and I already said this in the pre-introduction, but there's 3. You got your 3 major categories of plane patterns. You got your rosettes, where all the symmetries fix a point, like that one. You got your friezes, translational symmetry along one axis. I showed you this pattern, but did you recognize the flower it's made of? Indian paintbrush, yeah? And then you've got your wallpapers that have translational symmetry along 2 independent axes. These are the 3 main kinds of plane patterns. Oh, yeah, and that's a different pattern made out of my same streamside peach there. So now I want to start talking to you about how we classify patterns. And so there's value in a classification that you could agree, oh, we're both talking about a pattern of this type. There's actually an anthropologist who proposes using this categorization to keep track of anthropological artifacts that have decorative art on them. Yeah, so it's interesting. So it's also fun. So I want to classify patterns by the symmetries that they have. So this pattern has a lot of symmetries, and you could think, yeah, I'll just list all the symmetries of that pattern. Oy, there's too many of them. Because like here, if you put a square there to indicate that there is a center of 4-fold rotational symmetry, see the 90-degree turn all the way around, 90 degrees, 90 degrees, 90 degrees, 90 degrees. And so I could put yellow dots, but remember, this pattern is infinite. And so I'm not going to put all of those. There's also mirror axes. Did you see those? And there's too many of those to just write them all down. And then what else have we got? There's a glide reflection. Did you see that one? If you flip about that white axis and slide down, the pattern falls into coincidence with itself. There's actually one more that I haven't, a type that I haven't listed here. Center of 2-fold rotational symmetry right there. So you're not going to do anything by making a list. So the thing, if you want to get involved with patterns, is to start sneaking up on a thing called the group concept. And many of you are old hands at this, you know exactly about it. If you're new to the group theory concept, then this is the first best example that you always want to use to get involved with groups. And the idea is if you do one thing to the pattern and it didn't change, and then you do a second thing to the pattern and it didn't change, well, it didn't change the first time and it didn't change the second time, so when you do those 2 together, the pattern doesn't change. The composition of 2 symmetries is a symmetry. So I can start thinking which of those symmetries that I listed are sort of going to devolve from certain others. And that's what I'm thinking about freedom and constraint, is that if you're going to have this symmetry and this symmetry, then you must have the symmetry that arises from their composition. Like if you're going to have one translation this way, then you have to have 2 translations that way, and 3 and 4, and before you know it, you've got infinity in both directions. So if you want to become the person who can classify wallpaper, here's what you do. You learn how to draw a fundamental cell. And I have a handout available for this. I can email it to anybody who's curious or send it to your department. I didn't prepare them for this evening. But here's what you do is that you identify a center of highest rotational symmetry. So there's my 4 center. And then you find nearest translates of that. Nearest translates. And that is not a translate. Do you see why the little windmill goes the other way? Yeah, you could use a vector right-hand rule, and whoops, that's a left-handed one. So if you do this find the nearest translates, you will make a parallelogram. And that's the boundary of your fundamental cell. And then you identify other features. Parallel lines are for mirrors, but I'm not going to draw those lines to be the full length. I'm just going to draw them until they reach the boundary of the cell. So I should be drawing parallel blue lines there, parallel blue lines there. Where was that glide? Oh yeah, I'm going to use a dotted line for a glide going on there, but I'm just going to get in there, and I think that if I do that carefully, I'll get that. The diamonds are for centers of twofold rotational symmetry. And it takes some practice, but like I do a math circle activity where students draw a fundamental cell on a printout of one of the wallpaper patterns. And you will get one of these diagrams that looks like this. So you complete the cell diagram like that. And then here is an aside before we classify this one, is that it's a fact that this particular group, this one's called P4G. I use the notation of the International Union of Crystallographers. It's common notation. Some people turn up their nose at it because it's too popular. But anyway, I think it's a good notation. And here's a kind of mind-blowing fact, is that infinite group, all those translations, all those mirror axes, it can be generated by one mirror reflection and one rotation by 90 degrees, as long as the 90-degree rotation does not touch the mirror axis. One mirror, one 90-degree rotation, those two things in composition, compose them out, you generate the whole group. It's fantastic. So that's your homework if you're a mathematician, is go prove that that's so. But take it from me, that's how it is. So then we're going to say two patterns have the same type if their symmetry groups are the same. But by the same, I mean isomorphic is the fancy thing, but it's like you could take a checkerboard and then make a photocopy of it and enlarge it. And oh, well, that's just a bigger checkerboard. So, just different in that way. So first quiz question, the same type or different types? Votes for, everyone has to vote. Vote for, these are the same type. These are different types. Once again, everybody has to vote. These are the same type. These are different types. I tried to fool you by turning this on its side, but that's a fundamental cell. And there's a mirror axis that doesn't touch the 4-center. So because this has a 4-center, center fourfold rotational center, and a mirror axis that doesn't touch, it's the same group because they're generated by the same thing. These are both P4Gs. Same or different? This is your next quiz question. I wish I could say there were valuable prizes. Same. Different. One more time. Same. Different. Now, in favor of the same people, they both have 3 centers and mirrors. So, see, there's a mirror axis. But in between these 3 centers, these other 3 centers also have mirrors through them. Whereas here, that's a 3-center with no mirror through this. These are two different patterns. Here, and fancy language, in here, every subgroup that fixes a point has mirrors in it. It's a mathematical term, D3, dihedral group on 3 elements. Whereas over there, there is at least one subgroup that fixes a point that doesn't have a mirror axis, a cyclic group there. These are different, and okay, here's where I apologize on behalf of the International Union of Crystallographers. These are terrible names. P3M1, P31M. I think of this as more mirrors and less mirrors somehow. I'm sure it was very logical to someone, but it's horrible. But that's the hardest thing, though. All the rest of them are very natural names. So, and here's the source material for these. Point Lobos near Carmel, and flowers I grew 3 years ago or 5 years ago, something like that. So here's the surprise about wallpaper. We've seen 3 different pattern types. And, it's so creative with all the different things that could be involved in them. So how many of those could there be? Are there as many as human creativity can create? And keep in mind that people have been making patterns for millennia, and everyone who has a decorative culture makes repeating patterns like this. So there's a lot of human time to create pattern types, but there's exactly 17 of them. Who makes this stuff up? There is an analogous thing in 3 dimensions, 200 and some types of crystals that are possible. This is something very fundamental about the nature of reality that we live in. And there's no good explanation of why that number. You just have to go through and count them. There is a proof that walks through. I walk through a proof in my book. And here's the diagram from my book. These are the cell diagrams. So if you go through and draw your cell diagrams, you will find one of these. And like, for instance, there's P4G. So you draw, and you see that it's this one. And then it's very common to look at that and say, oh yeah, I missed a glide reflection, something like that. But then you see it and fill it in. And then that other question, these are the two pattern types with 6-fold rotational symmetry. And you can either have no mirrors and 6-fold rotational symmetry, or if you turn on one mirror, you get all those other mirrors all together. And you can't have 6-fold symmetry without 3-fold and 2-fold as well. Another homework quiz, just go prove that. If you're going to have one, no matter how creative you are, your pattern is going to have that other type. So to honor this amazing fact about our human world, I participated in the Chalk Slam at Carleton College. They had repurposed a local middle school as their art building, and bless them, they had preserved their slate chalkboards in every room. So they had a chalk slam, and so I participated by drawing the fundamental diagrams of the 17 wallpaper groups. And I had an art exhibition down the hall, so I could say, yeah, go find one of these. It's hanging over, and then once you start seeing them, you see them everywhere. So this is a screenshot from a very famous movie. And so you pause the movie and say, wait, no, I have to look at the wallpaper. And this also illustrates that a carpet on the floor counts as wallpaper. It's just a pattern that repeats in 2 independent directions. And then you sort of, don't get fooled by the hexagons. There's no 6-fold rotational symmetry there, just 2-fold rotational symmetry. Through points like that, you draw your fundamental diagram, and there it is. And then you look that up in the table and you say, that's PMG. That's one of my favorite groups. And what's the movie? Really? You're going to kick yourself. It's The Shining. Yeah? So the big scary hotel, the wallpaper in that movie is really astonishing. So, yeah, I really... I thought it said something under there. I would love for you to become the person who pauses the movie to look at the wallpaper. My husband makes fun of me, but I'll say, wait, stop. We have to, we have to look at that because it's just a beautiful part of human culture. So, okay, I'm going to maybe shorten this part about how the images were made. So I want to know, how do you take a photograph and use complex wave theory and turn it into a pattern like that? There are potentially infinitely many parameters to play with, so that artistic selection process is a very human activity. The basic ingredient is a humble plane wave. So I want you to think of waves as like the long waves in the ocean, not the waves that crash on the shore. Those become singular, and I come from the land of smooth. So I'm thinking of smooth waves like this. So just like this goes red, green, blue, red, green, blue, red, green, blue. And that's the basic ingredient. That's all these are. So the basic plane wave shows hues, and I want you to think of a color wheel where the hues go around from red, green, blue, passing by yellow and cyan and magenta on the way. So that's just, this visually is going that way, but it's also giving an output that sort of goes around a color wheel like this. So it's like that's my color wheel, and this wave is sort of progressing here while going around a wheel like that. This is the formula for it. If you like formulas, that's e to the iy. That's just proceeding in the y direction. That's the famous Euler formula, much beloved by mathematicians. So when I say complex number, you could just think, oh, he means a color. Okay? So a complex number and a color are in some sense the same way. And then, yeah, aside, that I've created over the years many, many ways to color the plane like a color wheel. And later I'll be wanting you to sort of remember about this stained glass window, created by a glass artist, Hans Schepker, based on my design from my work with color wheels. And there's an article about it in Focus magazine. Oops, I guess it doesn't say that there. So I do want to be talking about the words frequency and amplitude. And so I just wanted to show you what would it mean to double the frequency in this example. It sort of means twice as fast, and that would look like this. So when I think about a faster wave, it's just got, whoa, it goes regular, red, green, blue, red, green, blue, red, blue, faster. Okay? And then if I wanted to multiply a wave by half, I want to think of those colors as getting more toward the center and therefore more faded as you multiply by a half, and then getting darker as you go out to the outside. So there's this calculus of colors, this way of thinking of colors as things that you can add, and then things that you can, these waves as things that you can go more quickly. So if I want to superimpose 3 waves, this is the biggest surprise in the study of wallpaper waves, is that I want to think about a pattern with 3-fold symmetry. So remember those ones where some people thought it was P3M1 and some people thought they were the same and some different. How did I make those? I'm going to take a wave that goes this way, and I'm going to take a wave that goes 120 degrees, and I'm going to take a wave that goes 120 degrees like that. 1 wave, 2 waves, 3 waves. Add them up. I've referred to the idea that you can add these colors so that, red plus green plus blue would be exactly white. Well, the amazing thing, here's what you see when you will add those 3 waves. Oh, who made that up? Why is it that way? That is just this, for me, platonic suchness. It's this beautiful thing that is there for us to enjoy, that this is the superposition of those 3 waves. And, it might not be too surprising that, if you add red, green, and blue, you get white. So I'm suppressing a lot of details here. That oh, and yeah, here's a math slide for people who love math. Is that what these really are Fourier series? That you take a basic ingredient like that. The 2 pi I is because the n is a frequency in one direction, the m is a frequency in another direction. And so you get these waves. So each one of those individually looks exactly like that boring progression of stripes. But when you pile them on top of each other, you can get any pattern at all. The capital X and capital Y are adapted lattice coordinates for wallpaper with 3-fold symmetry. You've got to have an axis tilted like that. So the trick is then you take wave packets, and like I had 1 wave this way, 1 wave this way, 1 wave this way, I locked them together, meaning that I was always going to use those 3 exactly together. And then you superimpose those things. So wallpaper functions are built by superimposing locked packets of waves. The sum of waves formula produces an output of a complex number. The complex number gives you a color. So that's the mathematical background. And then how do we come to art? We say, well, why use colors? Why not use that as a diagram of colors? Where I had red, green, blue, why don't I just have this funny photograph of my shadow on a fall day when shadows were long? Turns into autumn moths. It's the same idea. You just put together a wallpaper function that has the right invariance, and then you play with the photograph until, suddenly those shadow pieces turned into bats. I like to think that, I love the patterns that I've made, but I want to see the patterns that you make, because I'm surely not the best artist working in this medium. So take that as your charge. This is a screenshot from Symmetry Works. There's just many, many different choices you have. This tries to make the choices easy so that someone who is not so oriented to mathematics can get in there and drag things around and see what happens to the pattern. Yeah, and what makes it art? It's the choice. It's the thought, this is the one. This is the beautiful one. Scientific American, for a blog site post, invited me to work their logo into a design. So I started with this surfer at Asilomar State Beach, and then see that glide? I think that glide is very cool. And then getting their logo to appear there in the bubble was a real trick. I want to show you just a couple of my favorite ones. Here's a minimalist one. You wouldn't think that just a photograph with so little color variation would turn into a great pattern. But this pattern has been very popular. There's just something about it. And so do you recognize P4G? Fourfold rotational symmetry and a mirror that doesn't touch the four-center. I hope you will see P4G out in the real world, now that you've learned it. And this is just a really weird one. I was cutting beets, and I realized I had caught myself red-handed. So I'm in the middle of this cooking operation, and I get my camera and, show my hand there. And this is just such an unusual, weird pattern. And this one illustrates how you have repeat symmetry in two directions with no rotations, no mirrors, no glides, nothing. This is just repeat symmetry. That one's called P1. It's down at the bottom of the wallpaper groups. So a twist is to have color reversing symmetry. I started with a color wheel, mainly a photograph, that it takes a photograph. I turned it upside down and negated the colors. So for people tuned into the complex numbers, there's the origin. And if you take a color and it's negative, those will have the opposite color. And that made this pattern. You might think that this is only a mathematical curiosity, but I was in a restaurant and looked at the wall and said, color reversing symmetry, oh my goodness. So just in case you didn't see it, if you reflect across that line, all the colors turn into their opposites. It requires a color reversing color wheel, so I took my window, this is why I wanted to tell you about it, and took its negative there, and then tried some waves, put it into the Symmetry Works software, tried, looked and looked and looked and looked, and turned it into this, which is one of my favorites. The way the positive colors pop out in front of you make those triskelions. So, now I want to talk to you about 3 variations on symmetry. These are things that have mostly happened since the book. And so this category is called imaginary landscapes. So it really is sort of a virtual reality kind of art form, and I'm yearning to be in an environment where I can see these things computed lifetime. But I'm going to tell you a little bit more about this. So I love the shape of my window, so I reproduced it and then made a collage using flowers and different, like the grass is trees, or the green is grass and trees, and camellia, rhododendron, Mariposa lily, and to create that. So I was very surprised about 3 years ago now when I upgraded my Photoshop, and there was a button near the top that, because I was using Photoshop just to manipulate the images and change the colors a little bit, try to make them look good. And there was a button on the top menu that said 3D. So like a good primate, I pushed the button. What are you going to do? And it opened up into this whole thing because there are ray tracing algorithms built into Photoshop. I mean, how can this happen? Back in the 90s, it used to be that ray tracing was available to the fanciest people at Pixar, and then here it's available to the home user. Now, I do have a really fancy computer that some of you have helped me lug around campus. It weighs a ton, but it's an Alienware machine. Any young people know what Alienware is. It's a gaming machine, and it's very heavy, but it's great. So what do? First, you create 3D virtual objects. And this I call this a shrink-wrapped polyhedron. It's based on which one is that? Great rhombocubooctahedron? And so that was made in Maple. So you create these 3D virtual objects, and then you can paste things onto them. So here, that's a photograph of my wood floor in my house, making that appear to have wood grain. And then this is made from that collage, the floral collage that I showed you, except that it's painted on a sphere with cube symmetry, because this thing has cube symmetry, so I wanted a ball that had cube symmetry. I put a copy of the ball inside of the weird shape and said, by the way, you are made of crystal. You can declare material properties inside Photoshop. I'm dazzled and amazed. And you could say, and floor, by the way, be really reflective. And then you can shine lights on them. So you can, tune the lighting so that everything is well lighted. And then on my fancy machine, it took about 24 hours to render this. So, it's the machine just going, okay, I'm figuring out where the light would go if there were a camera here, if these things were real. So I've been delighted by the possibility of creating imaginary landscapes, and that's all of them I'm going to show, because I want to save a little time to talk to you about Fibonacci spirals. So this is the pattern on my shirt. If you want to get a shirt like this, you can go to printalloverme, PAOM.com. You can upload your own wallpaper pattern or whatever pattern you wish. And you can, Alex was kind to mention that I had won an art prize, and it was for this piece. So yeah, you use what's called the complex exponential function to take a wallpaper pattern and wind it around into this particular kind of spiral. And I was inspired by John Edmark's Blooms talk at Bridges. If you don't know John Edmark, Google John Edmark Blooms. You will see videos that show you remarkable things. And this is duplication of what I said this afternoon, but the Sierra gooseberry is important to my family, let's say. We make jelly out of them and sort of laugh at our pain in picking these berries with thorns all over them. So the thing about it is that let me draw your attention to these 2 points. There's a very special angle here called the golden angle, related to the golden ratio. And if I were to rotate this image going from there to there, then I would see almost the same thing, but the thing at the top would be just a little bit bigger. Okay? So if I were to show you a succession of images computed from this same base image, then it would look like the thing was coming out at you and getting bigger, or blooming. That's what John Edmark meant by blooms. Who makes this stuff up? And then you can use these as functions on the Riemann sphere and then make shapes out of them. So here is a very weird thing. I've got a 3D print of this one, except I had to sort of tone down the extremely spiky stuff at the top. If you 3D print these things, you can actually strobe them and have them bloom like this. And then I think I showed some of these earlier today, so many of you have seen them. But this is like something coming out of one source and going into a sink there. And all made by this same technique of the trick of Fibonacci spirals. A thing that I've been doing lately in response to a question from John Edmark is that I've been morphing along those spiral arms, so that as things come out, they not only grow, but they also sort of morph and change. It's done by taking the source photograph and turning it upside down as you go along the spiral arm. And that looks like this. So that you can see up here these things, and there's a particularly fascinating ring there. So this is a pattern that is coming out at you and also morphing as it comes. So this comes into my last topic, which is vibrating wallpaper. So I don't think I'd like to live in a house with vibrating wallpaper. But it stands to reason that if you make things out of waves, those waves know how to move into the future. Fast waves move more quickly. Slower waves move more slowly. Each of these patterns is a superposition of waves. And therefore, I should be able to move that forward in time. It's for people who know the linear wave equation. These are just solutions to the linear wave equation. They know how to move in time. And you get a visual effect like this. They're maintaining the same symmetry, because the symmetry is like a property of the waves. But the variety of the pattern is changing because those waves are moving. I just have a belief that solutions to partial differential equations will inherently look harmonious, that this particular motion is going to look calming and lovely because it comes from solutions to partial differential equations. I had an opportunity to collaborate with a musician. I'm friends with Barbara Day Turner, the founding conductor of the San Jose Chamber Orchestra. She saw my work and said, oh, we've got to put you together with a composer and write a piece. Well, lo and behold, In a State of Patterns was commissioned by the San Jose Chamber Orchestra of composer Bill Sussman. I gave a talk at Bridges last summer, I guess, in Sweden, that because these are made of waves, there are frequencies that go with those waves, and so there are these weird scales that you can use. So that's what I proposed, is you use these weird scales that have notes that aren't on the piano, but he decided that no, he didn't want to use the special scales. He just wanted to write beautiful music, and I'm going to show you one of the movements. It's a piece in 6 movements where each one comes from a different photograph of California. California poppy, Sierra Nevada, that one with the sweet peas that you saw, and then Sierra tree death, another one with Sierra tree death, and then so the stars come out to comfort us. So here is the Sierra Nevada movement. It's about a minute and a half long. So there was a live performance of this, live chamber orchestra, and I was triggering the movies through PowerPoint from a laptop. So, like I said, it's surprised me how many possibilities. I thought when I started this that what I was going to do was make really nice diagrams for my students to look at wallpaper and study wallpaper. And it's turned into this whole amazing thing that's taken me many places, like to your wonderful campus, and put me in touch with really interesting people. So I like to think that, you know, there are people here who might become involved in my enterprise and become collaborators on this. So yeah, the question is, what will you create? Thanks.
Thank you for that wonderful talk.
Thank you. I'd be happy to answer questions.
So you're rotating the point, the plane there around a fixed point.
Yeah.
And so this kind of this optical illusion but it's simply a rotation.
That's right, through that special angle. And the trick is, and I think I told John something that he didn't know, is that you use a Fibonacci sequence of complex numbers that starts, it's the same Fibonacci recursion, but it starts with initial data 1i, and then that generates this, it depends, it's a long story, but it generates these special wallpaper patterns that there's 2 things about them, that when you wind them around, they match, and the second thing is that there is a translation so that when you go by that, or there is an angle, so that when you rotate by that angle, it's almost exactly fit, but it's off by just a little bit, and that little bit makes that expansion.
Because the angle seemed big, but it was many frames per, so it's just, that's the symmetry that we can't see.
Right, yeah, it would drive you crazy if you saw all the things in between, but we're only seeing this frame, this frame, this frame. And that's the thing about strobing these things, is you get a 3D print of them, and then you get the strobe so that it only flashes after that magic angle has passed. And this is what John Edmark's blooms are. He's got these boxes with a strobe light in the top, and you can just see these astonishing things that come out. Yeah, good question.
You mentioned math circles in passing.
Yes. I work with Tatiana Shubin with our Bay Area Mathematical Adventures series, BAMA. It's a lecture series, and Tatiana is, in a way, ground zero of math circles in the U.S. And I'm not very involved with them, but somebody asked me to do a math circle. And so this is an activity. I've got handouts for the activity if you want to try and do it. It's kind of fun. What's required is that the student can get on board with what's a translation and a rotation and so on, and try to draw a diagram like that. Sometimes more guidance is needed, sometimes less. Yeah, you had a math circle up here?
We have talked about one. I think Brad has had one.
Well, we have people who are interested in making them.
Yeah. Yeah, I'm not a great source on it, but Tatiana Shubin, she had the most interest. She's at San Jose State, and she had the most interesting sabbatical plan I've ever heard. She traveled around the Navajo Nation founding math circles there. And there's a movie called Navajo Math Circles that I would really encourage you to find and show as a club activity for a math club. It's amazing work. We have a VR lab at Santa Clara, and I participated in some meetings, and I kept saying to people, I see that sphere you got there, let me take this and put this on that sphere. And they go, yeah, well, we're too busy, and anyway, it's going to happen. It's got to happen.
We just opened kind of a lab in our library.
Yeah. Because the fundamental activity is that you define objects, and then those objects they have meshes, it's called, and then you can open up that mesh and paste visual information on it. So I've got the ways, the methods to paste stuff on those things. So I'm hoping that will expand.
So earlier on you had a slide with the Indian paintbrush
Mm-hmm.
on it, and when I look at friezes, I can't really help but cross my eyes just a little bit to see if I get a stereographic.
Oh, huh.
And the colors did kind of pop a little bit, but I was wondering if you could combine that with this golden angle business to try to get.
Oh.
I'm not sure what that would.
Well, I don't know if you can cross your eyes to make that go with that. That would be quite a trick. But early, I used to really love stereograms, and so early on I thought, oh, this is going to allow me to design the coolest stereograms, and then, it didn't. So, I mean, you can try, but yeah, we'll try. Well.